Hello everyone, welcome to Coders Camp. So we are today at the 10th day of May LeetCode challenge and the problem we are going to cover is count primes. So this problem is under easy category in LeetCode, but they have given around 8 hints to make us learn a new algorithm today. So the input given here is an integer value n and we have to return the number of prime numbers within the given limit n. So let's understand this problem with an example. So here is our given input limit n equal to 10 and we need to return the number of prime numbers within 10. Hopefully we all understand what is a prime number and within 10, 2, 3, 5, 7 are the 4 prime numbers and we have to return 4 as our output. So if we are trying to implement this in our program, we need to determine if a number is a prime number, then we need to check if it is not divisible by any number less than n. So if you write it programmatically, it goes like this. That is, we are going to iterate starting from 1 to the given limit n and check whether every number is prime or not using a function is prime. If it is a prime number, then we are incrementing the count and finally returning the result. And is prime works in this way. We are going to again iterate starting from 2 to the given number or passed number to the function, and if it is divisible by any of its previous numbers or any numbers less than the given number, then return false. If not, if the iteration completes, then finally we are going to return true. This is a straightforward brute force approach of this problem and it is going to work in big O of n square time complexity. So this is the first intuitive solution we all would think. The hint 1 and hint 2 talked about the previous solution we have discussed, and here comes our hint 3. It says if there is any number n multiplied by p into q, for example consider 12, in this case 12 can be a multiple of 6 into 2, 4 into 3, same way 4 into 3 and 6 into 2. So here 4 into 3 and 6 into 2 is again the repetition of the above two operation, just the interchangeable numbers. So in this case, we don't really need to check whether 12 is a prime number by dividing it with all numbers starting from 1 to 11. Instead, we can check only with numbers which are square root of n. So we are doing a little change to our previous solution, that is here in is prime function. Instead of checking for every I less than num, we are checking I into I less than num. So in that case, we don't really have to iterate all the numbers which is less than n, and this reduces n power 1.5 time than the previous solution. So this solution actually works in big O of n log n time, which is actually better than the previous solution. So here comes a hint 4 which talks about a most efficient way to find all prime numbers up to n. So we are going to discuss this approach now. So Sieve of Eratosthenes is one of the efficient algorithms to find the number of prime numbers within a given limit, designed by an old Greek mathematician Eratosthenes. So starting from 1, 1 is not a prime number, so let us strike it out. And moving on to 2, 2 is a prime number. So we all know 2 is a prime number, so let's leave this. So the Sieve of Eratosthenes says that if any n is a prime number, then all its multiples cannot be a prime number. So if 2 is a prime number, then multiples of 2 cannot be a prime number. In that case, we can remove them from the list. So I'm going to remove all the multiples of 2 first. So it goes like this. 4 cannot be a prime number. 6, 8, 10, 12, 14, 16 and 18 all goes away as they are even numbers and they are divisible by 2. So they cannot be prime numbers. So next moving on to 3, and 3 is a prime number. So as per this algorithm, it says if 3 is a prime number, then all multiples of 3 cannot be a prime number. So we are going to strike out multiples of 3 now. So in this case, multiples of 3 goes 6. 6 has been already removed. So moving on to 9 and 12 has been removed already. And then goes 15 and then 18 is already removed. So we have removed all multiples of 3. Then again goes 5. 5 is a prime number, so we are going to remove multiples of 5 again. So in this case, 10 is already removed, 15 is already removed, and we don't have any other multiple of 5. So again moving on to 7. So 7 is a prime number. In this case, we are going to remove the multiples of 7 from the list. In this case, 14 is being already removed and we don't have any other multiple of 7. And next moving on to 11. 11 is another prime number, so multiple of 11 not exist. Moving on to 13, 13 is a prime number. We don't have multiples of 13. And moving on to 17, 17 is again a prime number. We don't have multiples of 17 in this list. So in this case, what are the numbers left once we complete all the iteration? Is 2, 3, 5, 7, 11, 13, 17. So overall we have 7 prime numbers within the limit 18. So in this case, 7 is our output. So before getting into the coding part, let's understand the time complexity of this algorithm. So first we are going to iterate all the numbers given. So that is going to take big O of n time complexity. And once we encounter 2, we are going to remove every multiple of 2. In that case, we skip every 2 numbers. In that case, the time complexity is going to be n by 2. And when we encounter 3, we are going to remove every multiple of 3 and we are going to iterate through every third number, so which is going to reduce the time to n by 3. And when we go to 5, it is going to be n by 5. We are not considering 4 as 4 will be already removed since it is a multiple of 2. And it goes the number of prime numbers given inside the given limit. So overall, if we take big O of n as a common factor, then the rest of the time complexity goes like 1 by 2 plus 1 by 3 plus till the overall limit. So if you represent this form, then it is going to be big O of n log of log n. So this is like this part, fractional part alone will be represented as log of log n. So overall time complexity is n log of log n. So let's go to code now. So let us declare a Boolean array of size n. So this actually represents whether the number is a prime number or not. So if it is true, then it is a prime number. If it is false, then it is not a prime number. And int result, which is going to hold the number of prime numbers, which is what we are going to return at the last. So in between, we are going to iterate our given n starting from 2. As we know, 1 is not a prime number. And we are checking whether is not prime of I is false, then in that case it is a prime number. So we are going to increment our count. So once that number is prime number, we are going to delete or update the Boolean array to true that its multiples are not a prime number. So in that case, we are again going to iterate it starting from 2 and j star I is less than n. J star I is nothing but if I is the prime number, which is 2, then it goes 2 star 2, 3 star 2, 4 star 2 and find all the multiples till the limit. And it is going to update in this Boolean array j star I is equal to true, which means it is not a prime number. So yes, once the iteration completes, it will count only the prime numbers and finally return the result. So let's run and try the solution. Yes, it is accepted. So here comes our hint 6, where hint 4 and 5 talked about the Sieve of Eratosthenes algorithm. It says another clue that we can mark off multiples of 5 starting from 5 star 5 because 5 star 2, 3 and 4 will be already counted off. That is, if 5 is the number, then we will remove all the multiples of 5. So here's the multiples of 5. If you see, 10 will be already striked out as this is the multiple of 2, and 15 will be striked out as this is the multiple of 3, and 20 also will be striked out as this is a multiple of 2 again. So in this case, if we are iterating starting from 5 and check every multiple of 5 is not necessary as this numbers will be already counted. So if we are wasting time or wasting the iterations. So instead we can start directly from 25, which is actually 5 cross 5. And then we can continue our iterations. So this saves number of considerable iterations before the number I. So in the same solution, I'm going to update my j to I cross I as we are going to start our iterations from the square of the given number. And this is not needed as we are multiplying it, and I'm going to increment j every time by I. so that it is again a multiple of 5 starting from the square of that number. So I'm gonna update j is equal to true. So this is it. Let me run and try. So yes, let's submit. Okay, it goes out of bound for the highest number, so I'm gonna update my variables to long, and so let me try this. So yes, this works. Let me submit and try. So yes, the solution is accepted and runs in 29 milliseconds. So thanks for watching the video. If you like the video, hit like, subscribe, and let me know in comments. Thank you.